All right, so, well, I feel like I should probably give a brief introduction myself because I'm not actually from imaging science and I'm new to RIT. But I'm an assistant professor at the Sustainability Institute working on energy systems, mostly in sub-Saharan Africa. Simone is working on a project with me called eGuide, the Energy Growth and Use in Developing Economies Initiative, sort of a mouthful. But this is a collaboration between Columbia, Carnegie Mellon, RIT, and the University of Massachusetts. And what we do is try to better understand the demand side of the electricity sector by using data, with the goal of improving planning and operations of these power systems. Simone is leading the real imaging science part of this work. I won't upstage her and tell you all about that just yet, but Simone is a fifth-year PhD student in mechanical engineering at Columbia. She's just about wrapping up her PhD. She does work looking at electricity demand prediction and system planning. Before she was at Columbia, she did her undergraduate at Oregon State, did a master's at Stanford, then spent some time at IBM Research at the Africa Lab in Nairobi, working on healthcare and energy, and doing some really great work leading our efforts on electricity demand prediction using satellite imagery. So I'll keep it short and hand over to you, Simone.
Thanks, Nathan. I will share my screen now.
Great. Can you do that, or do I need to? There we go.
Okay. Hi. Just making sure. Can everybody hear me? Okay.
Perfect.
Good.
Yep.
Hi, everyone. I'm Simone Fobi, and like Nathan mentioned, I'm a PhD student at Columbia University. And today I will be sharing some of the work that's being done under the eGuide initiative, which again, like Nathan mentioned, is the electricity growth and use in developing economies initiative. Specifically, I'll be talking about our joint work in predicting levels of electricity consumption for residential buildings in Kenya using satellite imagery. Again, this is a collaborative effort with Nathan and some of our other collaborators at UMass. So satellite imagery is quite useful for our purposes, mainly because it can be used to fill in the gaps, especially for data constrained regions like where we work. Like Nathan mentioned, again, we work mostly in developing regions, and we are interested in understanding electricity consumption, sometimes agriculture, sometimes building footprints. And it can be quite hard to get access to the data that supports such studies. But satellite imagery actually lends itself to such problems because we get good spatial coverage, good temporal resolution, and good spatial resolution depending on the problem that we might want to solve. For example, the image on the left shows the VIIRS data set, which is 15 arc seconds per pixel, and that's quite good to understand nighttime lighting, whereas the picture on the right, which is at 50 cm, can be quite relevant when looking at building footprints, road quality, which are some of the questions that enable us to answer about electricity consumption. So we like satellite imagery mainly because of that. Specifically for my research, I would say I have themes along the lines of using satellite imagery and machine learning for different purposes. I've been them here into two categories. The first one, which is improving label data quality. We observed that for, again, the regions that we work in, which is mostly developing regions, there is a difficulty in getting good quality data. For example, we're trying to do a building footprint segmentation task, and it was hard to get high quality labels. One might think of open source labels like OSM, that might be useful, but those labels struggle from quality issues. They might be misaligned, they might be missing, they might be identifying the incorrect item or instance that you're interested in. For example, they might be on a tree if you're looking for a building. So this work really focused on how do we learn a segmentation task or a footprint segmentation task using noisy open source data. And the thought there is to support some of our efforts in developing regions. The other line of work that I've spent majority of my time working on is applying satellite imagery and some machine learning for electricity access. And that's mainly what I'm going to be talking about today. So a bit of background on the traditional way that electricity is provided is through a centralized grid. So we start off with generation of electricity at some facilities. It could be hydro. More recently, there's move towards solar, towards wind. So upon generation, the electricity is transmitted through high voltage transmission lines, where it is stepped down to some medium voltage lines. At that point, it can be fed directly to industrial customers or further stepped down and brought down to distribution level to the household. So that's what has been done. I would say most countries do their provision this way, but we observe that to improve electricity access, it can be quite expensive to extend low voltage, medium voltage lines to very, very rural communities. And this has opened up the space to the types of technologies that can support increasing electricity access. For example, you can have mini grids that support local generation and distribution, or you can have small solar home systems that provide solar lighting, or maybe a small panel that can support a TV, rather than doing grid extension. So the good thing about these alternative technologies is that it still gives access to electricity. People can still use electricity. It's just that the means of providing electricity is different. And the cost implications also for the utility also looks different. So from a research standpoint and also from a practical standpoint, the question becomes, can we identify who would be most suited, or what type of systems might most suit a particular user, and start to incorporate our understanding of consumption, our understanding of demand into how electricity access is planned. So I've mentioned electricity access planning, but I think it's worthwhile clarifying a little bit. For developed economies, when electricity planning is considered, it's mostly along the lines of how do we commit our generators. So for example, how many generators are going to be on at this particular time? How do we incorporate renewables into our grid? And how do we reinforce the existing infrastructure, for example, reinforcing existing transmission lines? For developing economies, even though these questions that are prevalent in developed economies are still relevant, the question of planning also includes access. So how do you increase the number of people that have access to electricity? And that boils down to, where do you expand to? So where are people located? And the second part is, how do you expand? Meaning, what sort of technology do you use to provide electricity? To bring that home, or to clarify a bit further, this is an electrification plan for a place in Senegal called Putu that was done in our lab here in Colombia. And each node here shows a population center, and the size of the node just shows the number of people in that center. And here we are showing the existing grid and how to do electricity access, or how to increase electricity access through different technologies. So some nodes are electrified with solar PV, some via mini grids, and some by grid extension. And the decision factor here is mostly, I'd say, a cost optimization coupled with how much would be consumed at the particular node. Okay, so with that in mind, our objective, or what I'd say our ultimate goal would be to predict what we would call the stable level of consumption that a residential building would have after 12 months of connection using satellite imagery. I understand that there quite some definitions here that are not clear. For example, what's the meaning of stable level of consumption? How do we identify residential buildings? Why did we say 12 months? But the objective, or my take towards this presentation, is sort of walking you guys through the process that brought us to the definitions that we make, and that might be able to shed some light as to how we define these and why we define it that way, and ultimately how we do at the task. So to do that, I would start by talking about the trends of consumption that we observed, how we do consumption estimation, and eventually how we do consumption prediction, which is very different from consumption estimation, but I'll also explain that. The bigger message here is that we want to be able to predict the consumption levels for individual buildings, because that would be helpful for system planners, for them to be able to discern their low consumers from their high consumers, and then better tailor the technologies for electrification to those consumers. So I'm starting off with the consumption trends. We're lucky enough to start off with a utility partner in Kenya that the utility in Kenya, Kenya Power, provided us with 135,000 thereabouts residential utility customers. We also had access to their locations and their bills. So these are postpaid monthly bills that show how much electricity in kilowatt hours for that month that a household or customer used. This sample of 135,000 customers is just 3% of the Kenya Power customers. So it's just a small sample of their data, but relative to what one would get openly, say, in surveys, it is significantly larger, one, and we have a means of getting some spatial information from these customers. So the very first thing that we did was just to understand how consumption evolves over time. And to the right, I show, based off of the data that we received between 2009 and 2010 and 2015, so 6 years worth of data, how consumption evolved. So here we can, by here I mean, sorry, the figure on the right, we can observe a decreasing trend, but it's important to understand why that is occurring. So a few things occurred during this period. One, Kenya Power significantly increased the number of connections of electricity connections that it made during that time. So by 2010, it had about 1.5 million residential customers, but by the end of this period, which is by end of 2015, it had about 4.5 million customers. So significantly increased the number of residential connections that it made. And we also observed that even though the number of connections increased, we are still observing this decreasing trend, which suggests that it is adding, or Kenya Power is adding new customers, but those customers are consuming less, which has this net effect of presenting as a decreasing trend. This at least was the initial starting place for us to say that we need to understand the dynamics of different segments, and this can also be relevant for the system planners. So to understand these dynamics of the different segments, we did a spatial segmentation, or if I may say, spatial classification of consumptions or of consumers. To do that, we first needed to identify urbanization levels in the country. So by urbanization levels, I mean urban, rural, peri-urban, and then we can understand how consumption varies in those places. We used 3 data sets: nighttime lights, population, and land use, as inputs to K-means classification algorithm. The modification that we made is we constrained the K-means algorithm to what we called consensus regions. So at the time, there wasn't any clear definition of like what is urban, what is rural, what's peri-urban, but there are some data sets out there that give their own definition of what urban was for Kenya and what wasn't urban. So we merged these data sets and found regions that were agreed upon to be in the same class, for example, urban. And when we did our K-means, we constrained it such that these consensus regions had to be kept in the same class, although other regions could be added within the class. So what that provided for us then was a 1 kilometer resolution urbanization map of urban, rural, and peri-urban. And you can see from the figure on the right that it sort of aligns with our general expectation. Urban sits within peri-urban, and that is within rural. So you have this gradual progression from urban to rural rather than a stark jump. Given our urbanization map and where we know the customers to be, we could then estimate the number of customers in each of these regions and then study their consumption based off of their level of urbanization. So when we did that, which is, in this particular case, I present urban and peri-urban merged as one, and then rural as separate. We noticed a few things. One, but before I explain what we noticed, there is a slight change in the view of the figure, in the sense that the x-axis shows the level of experience that customers have with electricity. So we consider the dates that they received an electricity connection, and then based off of their bill, we can figure how experienced they are with electricity. It's important to note here that we are looking at different cohorts of customers. And what that means is that these customers received connections at different times. So for example, people that are at the rightmost edge have had 10 years worth of experience with electricity, versus people that are at the leftmost edge have about a year, but when they receive the connection, the calendar year is very different from that set. So that's important to note. Anyway, from this figure, we were able to see that in general consumption grows over time, although it starts to slow down. As expected, the urban customers use more electricity. And what was surprising to us that the bottom quartile of customers consume less than 30 kilowatt hours a month, even after 10 years. So just to put that in context, in New York State, I think as of 2017, the average monthly consumption for a household was 572 kilowatt hours. So you can imagine how stark of a difference that is, even after 10 years of receiving a connection. So like I mentioned, the previous figure looked at different cohorts. So we wanted to actually understand the behavior irrespective of the cohort that you're in, so the connection cohort that you're in. Here I'm looking at, or I'm showing just the rural customers. The behavior, the trend is similar for urban customers, it's just a scaling factor. the main things to know here is that in general, consumption grows within the first 12 to 18 months of receiving an electricity connection. We also observed that the more recently connected customers, so the customers that got connections in 2014, 2015 consumed less than the customers that received a connection in 2009, 2010. And the more recently connected customers also plateau a lot sooner than the older customers. And why this figure is very interesting is we're going to try to exploit this behavior later on to use it for our consumption predictions. Okay. Having gotten a general sense of consumption trends, we then proceeded to do consumption estimation. I mentioned briefly that consumption estimation, at least in our minds, is very different from consumption prediction. So I want to clarify what that means. So we define consumption estimation as using an input from a certain period and making a prediction or if I may say, or determining the consumption at the same period. What that means specifically is we would use an image that was captured last year to make a determination of last year's consumption. It could be last year's average consumption, median, whatever, but the time periods would match. So this is it's a lot easier of a problem because we are just matching the image to the consumption year. And this can be quite relevant for operations. But from a planning perspective, we are more interested in consumption prediction. And how we define that is, if we use an image input from last year, we want to make a determination of this year's consumption. What that actually means, this is just an example, but what that actually means is that we want to be able to use images prior to when a place or a household received an electricity connection and make a determination of their consumption after they receive a connection. And that would be helpful for planners because they can determine or anticipate how much will be used once a connection is made to that household. Again, this problem is quite difficult, significantly more difficult than the other one, just because there's that mismatch in time. But for at least the rest of this portion of the talk, I'll focus on the easier task, which is consumption estimation. We just kind of wanted to start easy and then build our way up to the harder task. So we start off with the same Kenya Power data set, and we picked a low, we decided to do the analysis at a lower resolution, so 450 meters. What this means is that we group all customers within the same 450 meter grid cell and then calculate their average. Here we are assuming that that average is reflective of the whole 450 meter grid cell. That's just one assumption that we made for that. On the other hand, we get images from Digital Globe. Here, the Digital Globe images that we have access to are acquired at different times. So we need to get the proper tile given the acquisition date and match it to the consumption data that we have to be able to do a prediction. Again, for this consumption estimation exercise, we started with very low resolution, 450 meters. Is similar to VIIRS around the equator. So we put in a large landscape into some encoder, and we want to output the probability that this patch on average belongs to a low level of consumption or a high level of consumption. Now, in terms of what we mean by low and high, we had to pick some boundaries that would be useful to practitioners that would still give decent model performance, and that align generally with what practitioners would refer to. And in this case, it's the multi-tier framework. So the World Bank provides a 5-tier framework that almost shows sort of like levels of consumption. And a lot of people use it in their work. So that was another consideration. So in this particular case, we defined low as 3 to 30, medium 40 to 80, and high as greater than 90. The low consumers are quite interesting for off-grid opportunities. Like I mentioned before, when the cost of grid extension is quite high due to the wire cost, off-grid opportunities can be very interesting there. The high customers are also of interest because the utility cannot afford to not connect these customers. So these are places that the utility would want to connect by all cost. So at a low resolution, again, at 450 meters by 450 meters, when we are assuming that the average consumption of that grid cell is reflected in our data, then we observe that VIIRS nighttime lights and our daytime satellite imagery are almost comparable in their performance when determining high customers from, or when separating high customers from low customers. We noticed that as you move towards closer boundaries of kilowatt hours, so when you're considering low versus medium, the prediction performance suffers. However, the daytime satellite imagery still does better than nighttime lights. And this suggests to us then that the sensitivity of nighttime lights when the consumption values are so close is not as high as that of the daytime imagery. So for a first pass—
Simone, can I ask a quick question?
Yes, please go ahead.
Can you just maybe, I missed I remember you said the arc seconds, but what is the spatial resolution differences between the day and the nighttime imagery?
Okay, so the nighttime imagery, even though it's at 15 arc seconds at the equator, that translates to about 450 to about a 450 meter by 450 meter grid cell. The daytime satellite imagery is at 50 meter resolution, but we get a patch that covers 450 meters by 450 meters. So even though each pixel here is at 50 centimeters, we get 450 meters wide. So that would be ×2, would give us the number of actual array that we'll have for this.
Yeah. Now, I'm just curious if there's any correlation or correspondence between the lower nighttime resolution, spatial resolution, and its lack of sensitivity relative to the daytime imagery. But anyway, I was just curious about that difference. Thank you.
Yeah, I think that's a good question. At least talking with some people that have worked with nighttime lights, some of the suggestions have been that one, the values that we get access to are not over that wide of a range. I think it goes from like 0 to like 63 or so. So there's only so many points you can get in between. Two, at least again from those conversations, at those lower lighting intensities, the sensors struggle to pick up sufficient signals there. So hopefully that addresses that.
Thank you.
No problem. So from this consumption estimation, one of the things we noticed immediately was measuring consumption from satellite imagery is hard, which is expected. I mean, you're trying to determine what people are using in their house using a satellite image. It's not like you can see through their roof into their appliances, so that's expected. But we were still able to observe that there's a valuable signal in the daytime imagery, which we might be able to leverage for scalable consumption estimation. So going on to the consumption prediction work, which is where we want to be, our objective here again is to predict the expected stable level of consumption of individual residential buildings after 12 months of connection using satellite imagery. Hopefully, some of these will start to click why we chose those criteria. So I'll start off by talking about the stable part. Like I mentioned before, from our observations, we noticed that most of the growth occurs between the first 12 to 18 months, of which the customers enter what we call a stable phase. Now, to get the stable electricity consumption, we take all consumption that occurs after 12 months, and for every customer, we find that average consumption that they have while in the stable phase, and that's what we want to predict. So by taking the average, it still gives us a kilowatt hour value, but we need to be able to convert it to a level of consumption. Similar to what I've discussed previously, why we'd want low versus high to support planning, and also balancing our model accuracy, we ran some tests to be able to determine what the appropriate boundaries would be. So formally, for this problem, we defined just 2 levels of consumption under at least our eGuide umbrella. And we show how that aligns with the multi-tier framework that other people usually refer to. So here we define low as being less than 30 kilowatt hours average month, and high as being greater than 60 kilowatt hours. We have this discontinuous boundary here because we found that it allowed us to still do okay without necessarily losing out on identifying the low versus very high consumers. The data preparation stage for this part was a bit more intensive because even though we start off with the residential customers, we have to group them by building location because we want to do predictions for individual buildings. We group the customers by building location. We select single customer buildings, mainly because it disaggregates the issue of connection dates when there are multiple customers in a building. And then we calculate the stable electricity consumption. We are able to get the corresponding satellite imagery. And then what this yields is about 27,000 image consumption pairs. And the reason why we have this number is because we had to do some selection for the stable phase. We had to match or get images that occurred before the customer entered the stable phase. And then we also have the discontinuous boundary. So for the individual building, we take a way smaller patch. So this is a 48 meter by 48 meter patch that's about 96 by 96 pixels in. And we feed that to our custom model and that outputs the probability of it belonging to one of the classes that I've just defined as low or high. Here we apply standard approaches for, and all through really, standard approaches for splitting the data and reporting our results. Again, like I mentioned, we determined 48 meters just out of experimentation, custom tuned our own model and did some learning with some control for overfitting. But what's probably more interesting is what does that translate to? So here I show two figures. One is to the left is how we do when predicting low, and then on the right is how we do when predicting high. Before I actually explain the results, the thing to note is here I'm showing the probability scores that are output from the model. As you move to the right, you have increasing prediction confidence. And for each of these figures, I show the fraction or the percentage that are correctly versus wrongly classified. So the main things to note here is that we are able to get a better or higher percentage of correctly predicted or correctly classified customers as we move towards higher confidences. So I say everything up until 0.8 is really where you should be looking at. After that, the sample sizes are quite small. We also observe that we are better at identifying these lower consumers. And you can see that just by the fraction of the percentage of correctly classified in the bins. Overall, that translates to an accuracy of about 0.64, which is significantly lower than where we started off with in the estimation task. So as expected, we thought that as the problem gets harder, it becomes harder to get at these customers, but we're still able to pick out some signal for individual buildings. Now the question then is, what signal are we actually picking up? We performed gradient-based class activation maps on our two classes. And here I show some of those results. The main thing that stands out here, or before I explain it, is the reds are regions that are highly activated, whereas the blues and greens are regions of weak or lower activation. And this is just an approach for us to be able to tease out what our model is, what features within the image our model is identifying or reacting to for a particular class. What we observe here is that we have very strong activations for places that are predicted as high, that are correctly predicted as high, and there's weaker activations for places that are predicted as low. What that means intuitively is that there's a strong consideration for the building itself when predicting high, whereas there's consideration for context also when predicting low. Like I mentioned, the buildings received highest activation when the consumption level is high, and more context is activated when the consumption levels are low. Daytime satellite imagery has those relevant features for consumption estimation. We then tried to do our predictions for all of Kenya, and we leveraged a data set of building locations. It has about 12 million building GPS points. And so from these GPS points, we're able to get corresponding images, and using our trained model, we're able to make predictions for different structures. So here, I'm just showing some of the predictions based on the class. The blue pins are structures that we predicted low, and red are those we predicted high. Again, these are just some of those predictions. But what we ended up doing is, after we made the predictions for the about 12 million buildings, we aggregated them at a 250 meter resolution, so 250 meters per pixel, and created a 6-band TIFF, which we returned to our API. So from our API, you can get counts of each class in every 250 grid cell. You can get the mean predicted probabilities for that class and the standard deviations. The challenge that we faced here is that we're able to confirm the accuracy for the whole country, mainly because we just have 3% of the sample. So we can't do it for the whole country. Here I present like a countrywide view of our predictions. But rather than showing the 6-band TIFF, I condensed it a little bit. So here I'm showing the fraction of low consuming buildings. So we just take all our buildings and then find the number that were predicted low, and that's what's reported here. So the reds are regions where we have more high consuming buildings. The blues are regions where we have more low consuming buildings, and all at 250 meter resolution. So you can see that there are some strong areas of red here along the coast in some of the big cities, Nairobi, Kisumu. But then we have these mixes of blues and greens as we start to spread out, which shows that even at 250 meters, there's quite some difference in what people are consuming at those locations. So just as a quick detour here, I'm just going to show you our website, which is eguide.io, and you can access our API there. You can also read more about the projects and outputs people, but at least for these purposes, you can access our API. We have documentation as to our model, so you can kind of go through it. It would probably touch on everything that I've shared here. And you can access our documentation if you want to use it. There's a Jupyter notebook example on how it works and what the outputs are. So let me just go back here. And the main thought here is we really want to be able to support integration of our predictions into electricity planning tools and other use cases that we may not necessarily have thought of. Our focus now is on improving our model performance. So far, I've shown you that we use daytime imagery for our predictions, but we've started combining other data sets to support multimodal learning. And these are non-imagery data sets. They're like census data, surveys, mainly anything we can get our hands on that we think can boost our performance. And we test that to see how much better we do. The thing to know is so far these data sets, these auxiliary data sets are lower resolution than our digital globe imagery. So here I show some samples that we've put in and evaluated independently. The main things to note is that when we added lighting foil rooftop material, we got a slight signal boost, but we're hoping that as we run through these experiments and hopefully at the end combine the ones that respond well, we can move the needle by maybe a couple percentage points. The other thought towards improving our model performance is around the data size. So we did a little bit of evaluation to see how our model performance changes with the data size. The right side of this figure really remains unexplored, and one consideration to adding our data size is to leverage data from other countries. We've started working with data from Rwanda that has a larger number of samples. So it will help us with the data size issue, but it's also quite interesting because then we can start to answer questions around transfer learning and more generalizable models for prediction, for consumption prediction that can be leveraged in other countries looking to evaluate electricity planning and electricity access. So far I've talked about our consumption prediction work, and through our API, we're hoping that this will be incorporated into planning tools. We've started working with some on the ground partners that support off-grid efforts to see if our predictions can be helpful in identifying opportunities for off-grid models or off-grid technologies. We're also hoping that this will be relevant for utilities when considering how to design and extend their grid. And even beyond electricity access, we want to be able to evaluate our predictions and see the correlation between that and other measures of economic development, since that's an area of interest in the places that we work. I just want to take just a quick minute to acknowledge some of our funders, the Rockefeller Foundation, that's really been key towards our eGuide initiative, and also EASA that has supported me through my PhD. And I believe that's all I have for today. If you are interested in accessing our documentation or API, you can do so through this information. Thank you.
All right, thank you, Simone. Very interesting. I think we have some 10 minutes or so for questions. There was already one in the chat box, so maybe we can start there. There was a question: how did you approach hyperparameter optimization?
How did I approach hyperparameter optimization? There've been a mixture of ways depending on the hyperparameters. Some of it is just through what I'd call like a greedy search, as you put on, for example, let me take patch size, trying to identify, or let's say learning rates, for example. Some of it might be running jobs at different learning rates to find out which ways or which learning rates give the best results. There are also some packages that support learning rates, like finding the appropriate learning rates. So you can explore those packages to see if they're suitable. Some of it, yeah, so I'd say it's been a mix of just like a greedy search, me just running a bunch of experiments. Another is leveraging some existing tools towards finding, I'd say only learning rates maybe obey that that approach. The rest is just through putting on way too many jobs on our cluster.
Great. I see a hand from Anna.
Yeah, hi Simone. This is a very interesting topic. So my question was about granularity of the task. You know, you are trying to predict from quite a big image the level of consumption, but it seems from the gradient maps that the network is just trying to predict whether it's a rural area, you know, whether it has a lot of trees around and it's then assumed that it's low consumption, or it's like an urban area, it has buildings. And so my question is, did you consider, you know, looking, actually trying to detect the buildings and then identify what kind of a building, like what is level of consumption for this particular building, instead of for big image?
Yeah, so that's actually a really good question. And I really appreciate that question because it touches on a couple of months that I spent on a detour, not a detour, but trying to answer that question. So I'll start off with the portion on rural versus urban. At the 450 meter resolution, the impact of rural versus urban is stronger. But as you go down to the individual building, which is just about 40, yeah, that's about 15 meters, the impact of rural and urban becomes less. So when we do our individual building predictions, we're at a very small, we're way smaller patch. So we've decreased that impact. The second answer there is when it comes to electrification, at least in developing nations, it's very hard to decouple the effect of urbanization from consumption, just also because of how places have been electrified. So if you look at Kenya Power, for example, electrification started off in urban centers with people that were more likely to be wealthier. And then through, if I say support from the government, sponsoring larger last mile electrification programs, places in rural areas have been able to get connected. So these places that have gotten connected are not necessarily places that have sought out connections for themselves, but are places that have received connection because the government is going on large electrification programs. So the impact of urbanization still influences electrification, and it's quite hard to decouple it 100% from it. Now, the third point that you brought up, which is with the building identification, actually touches on the reason why I spent some time working, I don't know if you remember at the very beginning, on OSM building footprint segmentation, because part of or the thought there was, as we present a small patch to our model, we want to be able to present a mask that just has the building footprint. It's easier said than done. Why? Here in I say more developed economies, one, accessibility to high quality building footprints is very easy, and the quality of images that can go with the building footprint also reduces the hurdle of the task. So if you want to build a good building segmentation model, you need a lot of data and you need a lot of good quality data. Here you can get good quality data and you can get a lot of data. But as we move towards, say, Kenya, we struggled to get a lot of high quality labels to support proper building segmentation, which is why we then looked to OpenStreetMaps as an alternative. Now, when we got to OpenStreetMaps, it was riddled with its own issues. You had misaligned footprints, you had places that were labeled as buildings that weren't really buildings. You had an image that maybe 5 out of 10 of the buildings were had footprints there. So when you're doing a segmentation with that kind of data, you run into a lot of issues. And you can imagine that the issues would get exacerbated as you move towards more rural, unconnected areas where you are actually interested in estimating their consumption. So long story short, I find that to be a very exciting space of work. And yes, we are considering how to get proper building footprints when we are faced with these data quality issues.
Oh, okay, wow. Yeah, thank you.
Okay.
Nathan, this is Jan here. So Simone, have you started to consider maybe looking at, and you might have mentioned some of this, and I apologize if I missed it, but have you started to look into citizen type science, citizen inputs, you know, cell phone, geolocated cell phone pictures to help with some of this grid mapping and distribution mapping and so on?
So I haven't, but if you can point me to a resource, I would appreciate that a lot.
I was just thinking, and it's maybe worth mentioning to the imaging scientists on this session as well. So Nathan, as he introduced himself right at the beginning, is working on energy consumption prediction and grid distribution development and prediction. And I think satellite imagery especially, but also any type of imaging resource could potentially, as you just saw, play a significant role in this. So if anybody is interested in pursuing this kind of research and avenues, please reach out to Nathan, and he can also put you obviously in touch with Simone. But between us then as well, Brian Tomaszewski, I know in Golisano in computer science and so on, he works heavy in GIS, and I know he has a variety of projects in Africa coupled to some sort of citizen science approach using cell phone imagery and so on. And way back when we just considered this idea in context of disaster management, in other words, especially developing truth data for damaged buildings, damaged infrastructure, etc., from citizen cell phones, because you often need that kind of truth or tagging data to develop your algorithms and verify your algorithms outcomes. But I think in your case, it could also be a very useful type approach. And I was thinking of folks like in imaging science, Guoyu Liu is a professor, as well as Chris Kanan. They do quite a bit of work in Guoyu in 3D reconstruction from imagery using AI type approaches, and Chris Kanan heavy in AI and whatever that entails. I'm not an AI expert. So, but I think there could be a really cool sort of tangential pursuit here to say, can one use citizen science or citizen input imagery in an AI type system to develop rapid type products for either benchmarking or prediction or validating, whatever you want to call it. So, but I'll chat to Nathan as well offline and see. It could be a really cool project.
Yeah, I really appreciate that.
It was fascinating. Thank you from my side. Yeah.
Oh, thanks for having me.
Yeah, thanks for that, Jan. And absolutely, if there's folks on the call here at RIT that are interested in sort of the energy and development energy access space, I'd love to hear from you. I think we have a couple minutes if there's any last questions. And if not, we can leave it there.
Yeah. Thanks, Simone.
Thank you, everybody.
Thank you.
Yeah, bye.
All right. Yep. Thanks so much, everyone.
And thanks, Nathan, for arranging this. This was fascinating.
Absolutely.
Okay.
Yeah, we'll catch up offline.
Sounds good.
Great.
Thanks,
all right. Yep. Bye.